Welcome back. This is a short recording to finish off some of the theory that I wanted to actually cover in my very first recording. So we are kind of over our time limit a little bit, but this is a quick short recording. Let's say 5 to 10 minutes and we should be done. And then in the next recording I will hit the problems all related to this first part of this chapter. Okay, so this section is 6.2 and I'm sure, hold on one sec. Yeah, you probably were wondering, that was a long section, 6.1, right? Yeah, like I said, there's plenty to cover in this textbook in every chapter, so we do have to be a bit more cognizant of the importance of time. Okay, so 6.2 has 4 sections and I'll jump into the first one right away, and I must tell you the slide number, it's 25. Okay, so circuit symbols. This is the first time in our textbook he actually introduces these symbols. So far we've had the big blocks of P, N and P, but mostly in real circuit drawings we don't keep repeating those, we use these symbols. So on the left side we have the NPN transistor, and you'll see that the emitter is identified by the little arrow. And once you know the emitter, you can generally figure out the base and the collector based on the arrow. Similarly, for the PNP, the emitter, the arrow is shown, and you'll notice that the arrow is inward, it is pointing into the base, while for the NPN, the emitter is outward, it's pointing away from the base. Okay. Also, the reason we draw it with the the collector on top here for the NPN and the emitter on top here is because of this reason at the bottom. For an NPN transistor, the base and collector voltages are always higher than the emitter voltages. Remember, the emitter generally gets grounded, and then all the other voltages are with respect to the emitter. So that's why the higher meaning on top of the drawing, while the lower voltages are the below, right? Similarly, for the PNP transistor, the base and collector voltages are lower and the emitter voltage is higher. Okay, here the emitter is lower, here the emitter is higher in voltage, and that's why we use this convention. Okay, next slide, slide 26. Now you see to this circuit symbols of the PNP and PN, we start attaching the appropriate voltages. So you see the emitter base junction has the VBE, right? And this must be a forward bias junction if you remember. And the base collector junction has this voltage VCB, which we know must be reverse biased, and that's why the positive terminal is connected to the negative collector block, and the negative battery voltage connects to the positive base block. Okay, same, the opposite is true for the PNP. Okay, this is for active mode, by the way. Also notice how the directions are shown for the various currents. Here we show the collector current coming like this from the top, and the base collector coming in like this, and the emitter collector is leaving the emitter, right, into the external circuit. The opposite is true. Emitter current for the PNP comes into the device, the base current is leaving, the collector current is also leaving the device. Okay. Example on the next slide, 27, so we'll wait to do that. Here are some graphical representations. Now, as soon as you see this on slide 28, you may remember the same shapes for what we drew for the diodes and the PN junctions in chapter 3 and 4. That's because the basic relationship is still the same, the exponential relationship that connects the current to the base emitter junction voltage. Okay, we don't show the reverse, we don't much care about the reverse in transistor operation, but the forward looks like this, and you'll notice that 0.7 volts, which was the voltage drop that we assumed as a standard or cut-in voltage for most diode calculations, right? Also, the dependence of the temperature, because Vt depends on temperature, you'll notice that as the temperature increases, T1 greater than T2 greater than T3, you need lower VBE to get the same current. Okay. All right. The next chart graph is something called IC VCE characteristics. Right. Now, normally we think that the collector current is constant. It only depends on VBE, the forward bias junction voltage, right, of the base emitter junction. But in reality, so that's partly true that the IC depends on this, which is what you see here, right? On the right side, you see the graphs for various VBEs, right? You get different current. So the more the VBE, the more the current, but it jumps up like this, right? But in theory, because we are plotting VCE against IC, it doesn't matter what VCE is, right? It should be constant. But what we notice is that for any given VBE, so let's pick this, okay? VBE is, let's say, 5 volts. For 5 is probably too high, but let's say 2 volts. So for 2 volts, as you increase the VCE, the collector emitter junction voltage, there's a slight increase in IC, right? Not too much, but it does go from here to here, the slight increase. That increase was originally thought shouldn't be there, but then it was discovered by a gentleman called J.M. Early, and it's called the Early effect. So remember this is part of understanding the logic, and this variation is actually also important, is used later in amplifiers. But the bottom line is the current IC depends a little on the voltage VCE also, not too much, but a little. It's not shown here, but it does also, but that's a reality. This is because a higher reverse voltage increases the depletion region and decreases the effective base width omega W. This increases IS and hence it increases IC. So increasing VCE increases IS and hence increases IC. This was discovered by J.M. Early, and it's called the Early effect. Now there is also the saturation region shown where the behavior is different, and we'll talk about that a little more in the next slide and later when we actually study saturation a little more. So there's the same thing is shown here. Instead of showing a voltage source on the base, we show a current source, and you'll notice the shape is generally the same, but now we talk about IB instead of VBE here, right? Okay. And the saturation region is shown a little bit expanded. Let's wait another couple of slides. Yeah, next slide talks about saturation. So the term saturation is used because a change in the base current results in little change in the collector current. Here you can keep increasing the base current, but very little changes on the collector current. The VCE becomes a constant value called VC saturation, about 200 millivolts. IC begins to fall for VCE less than a certain value V1. So below this there's not much IC because it starts to get to 0 very quickly. And heavy saturation leads to a sharp rise in base current and a sharp drop in beta. So I saturation is very low, right? It becomes close to 0. And so how do you explain that? While base current is increasing because you keep applying more voltage, right, in the forward region, in the forward bias way to the other junction, the BC junction, so that current is increasing. So how do you account for the fact that this current IC, which is connected like this, is reducing. We say that the beta, which is like 100 or something, is being forced to a very low value, and so the beta forced is much less than beta. There are problems on saturation, so we can skip that. Yep, we come to this very last section that we have to study as part of the theory, and this is the only slide we need for this section 6.3, which says BJT circuits at DC. After this, we have a lot of problems to solve under this section, and the next few slides are all problems, and then we get to section 6.4, which we will only do in my next recording. 6.4 and 6.5 are introducing you to amplifiers, so we'll wait to do one more lecture on that. But for 6.3, we have a number of problems to solve. All these are basically about determining whether the transistor is in active mode or cutoff or saturation. And how do you determine that? You look at the values of the external battery voltages, the VBE, VCE that are being applied. We look at some resistances in the circuits, and then we look at IC, IE, etc. And then we say, okay, based on all this, we can say if the transistor is in saturation or it's inactive. All the relationships that I've taught you so far, they're all summarized here. So if you look at active, for example, the base to emitter voltage has to be 0.7, and the collector to emitter battery has to be slightly greater than 0.3. Anything above 0.3, you're still inactive. But on the other hand, if you are in saturation, then your VCE is less than 0.3, and it gets fixed at that value regardless of the external battery. And then it doesn't matter whether the first junction, the base emitter, is still forward bias, but because of the forward biasing of the reverse of the second junction, we go into saturation. So all this is shown. This is a nice table, table 6.3. It's pretty busy, but I do want you to pay a lot of attention and understand this, because this summarizes everything we have done so far previously. Okay, so this took almost 15 minutes, but the next recording will be about solving problems, and I hope to keep that to half an hour if possible, so that we are still on track for time. Okay, all right, let me stop here.